Right, Auto One, we're talking about basic electricity starting today, and we're going to be learning as much as we can about it. Electricity is one of those things that many people are afraid of, and I think that there's no need to be, as long as you understand it and know how to use it safely. And that's my job to teach you, so let's do it. So let's talk about all matter, which is made of atoms, which is made of protons, neutrons, and electrons. What we're really concerned about is electrons, because electricity is what we call, like it says here, the mass movement of electrons from one atom to another. Well, we don't really know what happens. Do the electrons move? Do they affect each other? Do they bump each other like dominoes? But we know it's some sort of a movement, or flow, we call it, of electrons, and that's how we describe it, okay? So electricity, as you know, doesn't flow through insulators like plastic, rubber, and ceramics, but it flows through conductors, metals, because metals and copper, gold, silver, metals like these have a large number of valence electrons, which is available electrons to cause electrical flow. Plastics, rubber, ceramics, things like that don't have valence electrons available to make them conductive. We use stranded copper wire in cars, because copper is a really good conductor. It's fairly malleable, so you can bend it and so on. And it's relatively inexpensive compared to gold and silver. Stranded copper, in other words, a 16 gauge wire will have, 12 to 20, I don't know exactly how many strands, which makes it super flexible for the vibration of the car. In residential wiring or household wiring, we use solid copper wire. This is solid copper ground. And this neutral and this hot, which is black, they're both copper, with insulation on them. But those are solid, and we do that because they don't need to be able to move around, because hopefully we're not having earthquakes that are big enough to cause that kind of a movement in our household residential wiring. So we're going to describe electricity in terms of three terms. So the first is current. So current is the flow of electricity. We call it amperage. So it says the mass flow of electrons through a circuit. That's more of a technical definition, but it's the flow of electrons through a circuit. We call it current or amperage. Amperage because the units is amperes. We just abbreviate amps for short, so we call it amperage. But current is the quantity or volume of the flow of electricity through a circuit. And a circuit is a path for electrical flow. And in cars, a circuit, and most all electricity, the circuit or the path is stranded copper wires or wires of some sort. So that's our path, coming from a power source on a battery through a circuit and then back to the battery. So current is rated in amperes, like I was saying. We just call it amps for short. All of your breakers on your home panel are rated in amps, either 15 amps or 20 amps, unless you have a heavy amperage circuit for a hot tub or an electric range or some sort of electric dryer, some sort of high amperage electrical device. Otherwise, everything's 15 amp and 20 amp. Voltage is the push on the current, or the electrical pressure, it says, which moves electrons. So we say voltage is electrical pressure. It's how hard we're pushing on the current. So cars have batteries that are 12.6 resting volts. Alternators produce somewhere between 13.5 and 15 volts, depending on the car. At home, coming from PG&E, you have two wires coming from the pole or underground if you live in the arbors or somewhere newer like that. Two wires coming to your house that both have nominally 110 volts, although like at my house, they're both 121. I've got two wires, or we call it two legs of 121 volts. So it'll be somewhere between 110 and 120 volts AC. Automotive batteries produce 12.6 volts DC. Automotive alternators produce between 13.5 and 15 volts AC, but we'll talk about that. Actually, sorry, that's we convert the AC voltage into DC, so we say 13.5 to 15 volts DC. Sorry, mistake there. So voltage is electrical pressure which moves or pushes on electrons. It's rated in volts. That's our unit of measurement. And then finally is resistance. And resistance is opposition to current flow, holding it back. So current is the quantity of electricity flowing. Voltage is the pressure pushing it. and resistance is opposition to current flow, trying to impede or stop the current flow. And that's rated in ohms. Now, current uses a symbol I for impedance, not C, because C in physics is a constant. So we use another term that means a current flow or amperage, which is impedance. So I for impedance. V, we don't use V for voltage because V in physics is velocity. So we use, for voltage, we use the symbol E, which is short for electromotive force, or EMF, electromotive force. So an electric push force. And then in resistance, we use the symbol R. So I, E, and R are the symbols when we put it in Ohm's law and relate those terms together, which we'll talk about in a moment. So my explanation for current, voltage, and resistance is, let's say I've got a garden hose. I don't have a garden hose here, but I'll grab a vacuum hose, okay? And we'll say this is a garden hose and it's spraying water, and one of you is talking too much and we're sick and tired of you talking, so we're going to take this hose and we start soaking you down with water, okay? The amount of water that hits you, the quantity, that's the current. And I'm just making an analogy between electricity and water. That's the current. So you're getting just soaked with water. Well, the quantity that hits you is the current flow. How hard the water is coming out and pelting you in the forehead between your eyes and you're hitting me is what we call voltage, or electrical pressure by analogy. So the water pressure, which is in San Luis, it's city, the water pressure comes from pumps that the city has. And usually it comes to your house somewhere between 40 and 60 PSI, some places as high as 80 PSI, pounds per square inch. So how hard the water is hitting you, that's the voltage or the pressure. And then one of your classmates feels sorry for you getting soaked, so they come and stand on the hose behind me, and all of a sudden the water trickles down to nothing and you're not getting soaked anymore. Their weight on that hose represented a resistance, which stopped the current flow. So resistance impedes or holds back or opposes current flow. And there's a little analogy to water, okay? So let me put this back up here and let's continue. So we organize electricity into circuits, which are paths for electrical flow, like it says up here. And those circuits consist of stranded copper wire, etc. And I'm going to talk about that right now. So you've got a power source, which when you start the car is the battery, and once it's running is the alternator, is charging everything. At home, your power source is coming from PG&E. You've got, like I said, a battery or a generator. A generator just means a device that makes electricity. In an automobile, that device is called an alternator. It's an AC generator. It makes alternating current, and then we convert that through a series of diodes into DC current, but we'll talk about that more later. So you have to have, in every circuit, you're going to have some sort of power source. Then we're going to have loads, and loads are something that we want to power up, something we want to turn on. A stereo, a power window motor, windshield wipers, a horn, heated seats, whatever. Those all are what we call loads that are devices that we want to power up to be able to operate. So every circuit has a power source, every circuit has a load or loads, every circuit has conductors, which is our stranded copper wire, and we say that we have an insulated circuit. The insulated circuit is the hot side of the circuit, so that's the power coming from the power source, and we put a plastic coating on it like we have on these wires. We put a plastic coating on those wires so that they are insulated from ground, meaning they don't touch ground, so the electricity isn't going to go through this red plastic coating over that wire. Further, we've got, like it says, stranded copper insulated wire for our positive side. I'm going to grab another harness over here if I can. It's going to wrap around this thing. Almost got it free. Okay, so this harness here, all these wires here, are 14 and 16 and 18, actually in some are 22 gauge insulated stranded copper wires. Okay, so that would be our insulated circuits, the hot side. The ground circuit would be the return path to the power source, the battery, the alternator. So it's also stranded copper grounding wire typically. Sometimes we would use a one-wire circuit in the past where we would return back to the battery via from like the rear of the car where the lights were, by attaching to the frame and then just having a wire at the front of the car going from the frame to the battery. Okay, so we've got an insulated circuit, we've got a ground circuit, and those provide the paths for electrical flow. So every circuit has a power source, some loads you want to power up, and wires to and from the power source to the device. Then we need some sort of control. So we're going to have a switch, whether it's mechanical or electronic. Mechanical would be like an on-off switch that you push, or a momentary on switch like a horn button. And those are mechanical. Or an electronic switch like a transistor, where we can use electricity to turn on a high current circuit. Okay, so some sort of circuit control. And I just put a picture of a switch here on a regular household switch. So next, we size wire. The wire that we use in a circuit is sized for load, meaning it's sized for the quantity of current that's going to be flowing. The more current that flows, the hotter the wire will get. So current flow causes heat. The higher current flow causes more heat. Smaller current flow causes less heat. So the more current that we need to flow, the bigger the diameter of the wire, or the cross-sectional area of the wire that we have to have. So larger diameter wire has lower resistance and can flow higher current, and also has more surface area to be able to conduct the heat of that current flow. Longer wires have greater resistance because it takes, as the current goes through, there's more oppositional resistance in that metal copper stranded wire. So every metal has some resistance, and the more distance of wire, or length of wire that you put current flow through, the more resistance it encounters. Wires are color coded, so we can locate them in wiring diagrams, or so we can see where they go in the circuits, and also so we can trace them through the car. So we can get on a Mitchell Protoman wiring diagram, we can see the path where the electricity goes. It goes through this fuse and this relay and this switch and to this device and then to ground, etc. And they're color coded both on the wiring diagram and on the actual insulation themselves. And I'm pretty sure you noticed all the different colors there that I have on these wires, so I can trace these wires through the car. And if you look carefully, like that yellow wire has a little yellow with a green stripe. Okay, so they would put Y/GR, which means yellow with a green stripe, on the wiring diagram. Primary wire, two types of wire in cars. Primary wire are low voltage 14 to 16 or 14 to 22 gauge wires, which are these low voltage wires. The maximum they're usually carrying is 15 volts. And then secondary wires are high voltage wires, and we only have this on some cars today, but mostly older cars where we had spark plug wires. They were thick insulation wire to be able to contain thousands of volts of electricity. Spark plug wires can hold 30,000 volts. And I have 30,000 volts going through them, but very, very low amperage. It will shock you, but it won't hurt you. And it can't cause you to lock onto it and be electrocuted. It just gives you like a very strong static shock. And it's kind of fun to shock students and just see how they like it and what it feels like. I know you think I'm sadistic. Anyways, so primary and secondary wires are two different types of wires in automobiles. The only difference to this would be when we get into hybrids or electric cars, when they have 400 volt circuits, and then our wires may have a lot more insulation on them, or they are going to be in different color looms and things like that, but that's for another time. So continuing to talk about electricity, I put some pictures here. First, just a regular switch, which is going to give us some control, like this home, what we call Decora switch. These are single pole switches, just on off is what we call them, single pole. These allow a circuit to be turned on or off, just like the lights in the room. Then we can have what's called a relay, and this is a relay here. And a relay is an electrically operated switch, which on the inside looks something like this. I'll try and get it to focus on there so you can see it. Yeah, there it goes. So what it is, it has a big coil. You can see the copper coil in the center that creates magnetism, and then there's a pair of points in here. So a low current circuit, as I drop it, grab another one, a low current circuit going through that coil of wire pulls these points down. There's points on the top, and I don't know if you can see them moving, but they're right there. right here, my index finger right there is pushing on the points. And so what happens is we put a little electricity through these two terminals, which creates um, a little current flow and magnetism, and then pulls the points down. So what we use a relay for is to use a small amount of current to turn on a high current circuit. So let me give you, for instance, a horn may flow 3, 4, or 5 amps or something. Well, we don't want that much amperage going through the steering wheel because the problem with that is it will give us potentially the opportunity for a fire. So what we do is the relay, when we push the momentary on switch, the horn button, it causes a very low amount of current to flow through this relay. And what limits the amount of current is the number of windings of that coil, because it has a fairly high resistance, so that you get enough coil of copper wire, and it is insulated. It's got plastic coating on it, so the little windings don't touch each other. Usually they'll have like 120 ohms of resistance. So if I look over here on the whiteboard, and I know that E equals IR, which means, remember, E is voltage, current, resistance. So voltage equals current times resistance. And let's say I've got a 12-volt circuit, from the battery, and I've got 120 ohm coil in my relay. So if I divide each side by 120, this is going to be 1/10. So I've got and that's amps. So I've got 1/10 of an amp flowing through that control circuit. So only 1/10 of an amp is flowing through the switch when I push the horn button. And so what happens when I do that is I will turn on a high current circuit by pulling the points down, and now 5 or 10 amps can flow to the horn and honk it, and everybody's happy. Or people in front of you, I guess, aren't happy. Let's keep going here. So I'm going to pull this a little closer. Okay. So next we got some circuit protection devices like fuses. A fuse that you see in these pictures, an automotive fuse is a replaceable fuse. They burn and then they get thrown away, and they're only a dime a piece or something like that. But a fuse exists to protect a circuit by burning out when the current exceeds limits, meaning like the wire insulation comes off and it touches ground, or something happens that we get too much current flow. So instead of melting the wires, we're going to burn the fuse. And I'll hold up a couple of fuses. First, this is just a standard size automotive plug-in fuse, and I'm trying to get the thing to focus on it. Let's see if it will. No, not yet. So you can kind of see the element in the center. I'm not sure why I'm having quite so much trouble getting it to focus. Oh, there it goes. So now you can see the element in the center. Here's a larger one. Got to put my hand behind it, and you can see that one's burned in the center. So the current flow was too much. Look at that. You can really see that. That's nice. And it burned. And then we have some really itsy-bitsy fuses like this one. These are real tiny ones. Let me see if I can get to focus on that element there in the center. Probably just a little too close. There it is. You can see the element in the center. It's actually burned apart. So what happens is, I told you that current flow makes heat. So when too much current flow goes across that little element, it just melts it and it burns it. Okay? So that protects the circuit from melting wires. Instead, we burn the fuse. Okay? So at home, you've got circuit breakers. And circuit breakers are resettable, current-sensitive switches. And they will kick off if you draw more current than it's rated for. You can see right here it says 20 amps or 20. That's a typical kitchen breaker or a bathroom breaker or maybe a garage. It's a max rated at 20 amps. And if you turn on too many devices that pull more than 20 amps, it's going to kick that breaker off, and then you have to reset it by flipping it off and all the way and then back on to get it to work. In cars, we have circuit breakers that are heat sensitive, but they expand away and then they expand back. So if you have, and I'm looking for one right now, I had one sitting here. Now it has eluded me. So my little power seat circuit breaker is missing at the moment. Anyways, I will not look much longer. I'm sorry, I had it right here and I set it aside. So what happens, we use a bimetal arm, which is two metals, which has a fairly high expansion contraction rate. As current goes across, if current flows too high and too long, it'll expand apart, breaking continuity. The load is no longer powered. This thing cools down, and then it contracts and goes back together, and then it reconnects, and current starts flowing again. Okay. All right. So we use those in power seats. We use them in power windows where you'll see them, and you'll see these on the interior fuse panel. They look about, they're about that wide and about that tall. And like I said, again, I had one sitting out here ready to show you, and it has vanished into thin air. Take one more quick look. I do not see it. Okay, let's continue. So, okay, next is electronic components. And electronic components are small, very, very small components that don't have any mechanical moving parts. So electric components are components that operate off electricity, but don't have any moving parts. And they can be a switch of sorts, like a transistor, or a one-way check valve, like a diode, etc. So a transistor, which is an electronic switch, it can be used, it's a low current switch, turns on a high current switch, and it can be used to turn devices on and off. A diode is a one-way electronic valve. A diode, like in an alternator, can be used to help convert AC electricity into DC. So we have transistors in cars that are a huge part of automotive computers. We have diodes in there as well, etc., etc. Diodes allow current to flow in one direction and not in a second direction. So they are a current control device. Then we also have what's called capacitors or condensers. And these are little electronic storehouses, little devices that can store stray electricity or absorb unwanted electrical surges, like it says. So inside this Toyota Tacoma automotive computer, we've got diodes, we've got transistors and capacitors and chips and all kinds of things soldered all together. That's a Toyota Tacoma engine computer, and it's they work very dependably. They are very consistent. They're not nearly as powerful, let's say, as your PC or your laptop, but they do what they do well, and they're a dedicated computer type machine. So those are electronic components, all those transistors, diodes, capacitors, or condensers. Finally, circuit problems is the last thing we want to talk about in basic electricity. Circuit problems, and maybe it would have been better to put this right after we talked about what a circuit is and how we form them, but circuit problems exist like this. First, we have what's called a short circuit. Short circuit is when a load is bypassed. So I'm going to draw a circuit over on the whiteboard over here, and I'll move you guys over here with the screen. But a short circuit is when we get, for example, the insulation on a wire rubs off because of vibration, and the wire touches ground, and now we've bypassed the load. So we'll just make a real quick circuit. So here's a 12-volt automotive battery going to a fuse, going to, we'll do a horn circuit, so this will be a momentary on switch, going to a horn, that little box is our horn, and then going over here and back to the battery. So what happens is, when I push down on this button, I connect these two terminals, and current flows through the horn and back to the battery, and we honk the horn. If this wire breaks here and touches ground, and that's a ground symbol because I've worn through the insulation, now current can flow through here and go metal and go back to the battery. Now there's no resistance. This has electrical resistance. There's no resistance in the current in the circuit now. So high current tries to flow, and it'll burn this fuse apart. If the short happens here, and this happens, then we're going to melt this wire. Okay, and I'm going to melt the insulation off almost instantly and burn the wire. Okay, so that's a short circuit. We say the load is bypassed, like it says there in the PowerPoint. The load is bypassed. We also say, consequently, resistance drops because the horn's not in the circuit anymore, so or probably not in the circuit anymore. So we've got the load bypass, we have resistance lowered, and we have high current flow. And when we get high current flow, we're going to make heat, smoke, and fire. Okay, we're going to burn things. Okay, teenage boys love that. I don't know why, but anyways, we're going to get heat, smoke, and fire. That's a short circuit. All right, so it's going to burn a wire, it's going to burn a fuse, or trip a breaker for at home. Our next problem is an open circuit. And an open circuit, or a partial open, is when a circuit gets broken apart, so there's no more current flow. So we say that resistance is infinite because we got a big air gap. We've torn wires apart, and we say that reduced or no current flow, and I'll show you this. Actually, I'll leave it there for a second for those of you taking notes. So an open circuit is where we have a big air gap, we have real high resistance, and no current flow. Okay, so we come back over here to the board here. So we'll just get rid of our shorts here. That didn't work out too well, did it? Anyways, we'll go like this, get rid of that. Okay, now we'll go ahead and put this back together. And we'll get this back together. And put that back together. So now, if we, something happens and this gets cut, and now we got a gap there, or over here it gets cut, or inside here somehow it shorts, it burns up, and now there's no connection. Current can't flow through when I push down on the horn button. In either of those three cases, current can't flow. We say resistance has gone infinite because we have an air gap. There's no current flow, and obviously the circuit's not running. So many people say to me, Mr. L, my such and such is not working. I must have a short. And I say, well, if it's not coming on, for sure you have an open circuit because no current's flowing. Now, it may be an open circuit because something malfunctioned, high current tried to flow, it burned a fuse or popped a circuit breaker, and now you have an open circuit. So you might have an open circuit because you burned it open, and that's being caused by a short circuit. Anyways, so a short circuit or an open circuit are essentially our two basic types of circuit problems that we'll leave for you at this point. All right, that's all we have.